In our last meeting, we looked at the electric fields produced by charged insulators. Charged insulators with a high degree of symmetry, that is. This time we'll explore the electric fields surrounding conductors. So let's start by quickly reviewing the difference, between a conductor and an insulator. No, not that kind of conductor. When we talk about conductors, conductors are a class of materials where electric charges move easily in response to an electric field, thus allowing for electric current. Insulators, on the other hand, are materials where charges don't move easily, thus not allowing an electric current. So when we talk about a conductor being in electrostatic equilibrium, and we'll use the symbol EE for short, just because, hey, it's a lot of writing time and we got other things to do in life. Okay, well, let me ask you to first, think back in your course of mechanics. Think to what we meant when we talked about static equilibrium. Okay, not electrostatic equilibrium, but the meaning of static equilibrium when we talked about motion. This was the condition where an object at rest remained at rest, where its motion didn't change. The cause of this, you recall, was that the net force on the object was zero. When we speak of electrostatic equilibrium, we're referring to the condition where there exists no net motion of charge. Now, charges may have some random thermal motion, but there is no net motion in any preferred direction. When I talk about random thermal motion, these charges may vibrate back and forth, but because they do so randomly, there is no net motion in any preferred direction. And let me just say this, just like the case for mechanical equilibrium, electrostatic equilibrium requires that the net force acting on the charges must be zero if their motion doesn't change. Today we're going to talk about 5 properties of conductors in electrostatic equilibrium. We'll start by listing each property, then try to explain what is meant by each property, then attempt to provide a proof or at least a justification of each property, and finally we'll look at various examples to see how each of these properties can be applied. So the first property we'll take a look at, regarding conductors in electrostatic equilibrium is this. It turns out that the electric field is zero at all points in the conductor when it is in electrostatic equilibrium. So if we try to explain, what's going on here, let's start by considering a conductor in a uniform electric field. And this is exactly what a parallel plate capacitor will provide you with. So, and we're going to do a whole unit on capacitors, but for now, let's assume that we have these 2 equal and oppositely charged plates providing a uniform electric field in the region between the plates. And let's suppose that we put a conductor, in this region where there's a uniform electric field. Now, it should make sense to you that because this is a conductor, and you remember this concept of charging by induction, because it is a conductor and those charges are free to move, that conductor is going to become polarized, and a charge is going to be induced on the surface of each conductor. So you'll notice here that, on the left-hand side of the conductor, the electrons will migrate to the left-hand side, to get to be closer to the positively charged plate, leaving the right-hand side of the conductor with a deficiency of electrons, leaving it a net positive charge there. So the end result then, is that the electric field inside the conductor, what I'll call E internal, gets established, which opposes the external field. And it turns out that, okay, the charges are going to continue to move inside that conductor until that internal field is exactly equal and opposite that external field. Okay, but once that happens, okay, then we would say that the state of electrostatic equilibrium is reached. So we're saying here that okay, the total electric field in the conductor is really a combination of the external field provided by the capacitor plus that internal field, okay, which is due to the polarization, okay, induced by that external field. And like I say, these two electric fields will cancel. It will not happen instantaneously. It will take time for this to happen, okay, but those charges will move until this state is reached. All right, so I just want to make a point that may be obvious, but maybe not. In the previous slide, of course, I drew this conductor to have a high degree of symmetry, but it really doesn't matter. No matter what conductor you put in that uniform electric field, okay, that internal field, the field established within the conductor itself, okay, will exactly cancel out that external field, okay, when electrostatic equilibrium has been reached. And I just want to point out here that electric field lines are continuous. So those field lines from the capacitor that go from one side to the other, they don't stop when they get to the conductor. Okay, they don't cease to exist, when you place the conductor inside. The fact that the electric field is zero inside of the conductor, it is so simply because that internal field is established that opposes the external field. So, remember the electric field is a vector quantity, and you can have field cancellation, okay, rather than field disappearance. So let's take a look at a very simple and elegant proof of this property here. And I just want to point out here that the general form of this proof, and we're going to employ this again, and if you've taken a course in philosophy course in logic, then you'll probably be very familiar with this. But what we're going to do is we're going to assume the opposite of the premise, the opposite of the hypothesis. Okay, in this case, the opposite of the property that we're proposing, and show that it leads to an inherent contradiction if we do so. And therefore, okay, by assuming the opposite, showing it leads to a contradiction, okay, this means that the original premise, the original hypothesis must be true. So here it goes. Okay, given that we have a conductor in electrostatic equilibrium, okay, let's assume that the electric field is not zero inside the conductor when it's in electrostatic equilibrium. So you see how we're really assuming the opposite of the property. And we're now going to show that this leads to an apparent contradiction. So let's take a look. What would the consequences of this be if the electric field was not zero inside? Well, that would imply that the charges within the conductor itself, okay, would experience a force, okay, equal to the charge times the electric field strength inside if it was not zero. Okay, because charges within the conductor are free to move, then we know, according to Newton's second law, that the charges would accelerate as a result of this net force acting on them. Therefore, okay, that violates the definition of electrostatic equilibrium. Therefore, the conductor could not be in electrostatic equilibrium. So while this doesn't give a mechanism, okay, it does tell us then, okay, that we can rightly conclude or infer that, okay, the electric field must be zero inside the conductor if it's in electrostatic equilibrium, if this contradiction cannot exist. So in this slide, I just want to clarify what it means to be inside the conductor. And so we'll do this through an example here. So if you take a look at the diagram I'm showing you in the right-hand portion of the screen, the conductor is the gray part you see. So let's assume that is a metal, for example. And I'm saying inside here in the very center of that conductor, there happens to be a negative charge. Okay, and obviously we have some charges I'm not showing you outside. So the electric field that I'm showing you, there's an electric field in the region, outside of the conductor. And when I talk about this region here, you may say, oh, well, that's inside the conductor. And I get that, but that's not what we're talking about here when we say inside a conductor. The material of the conductor, the metallic atoms, is only the gray colored area you see on the screen. So what I'm saying is that, the electric field inside of the gray area, where you actually have the conducting medium, the electric field there must be zero. Although, because there happens to be a charge inside here in this hollow cavity, well, then the electric field doesn't have to be zero inside of that hollow cavity. So I guess my only, not to confuse people, but you may consider this region in a colloquial sense to be inside the conductor, but I'm talking about really inside the conducting medium itself. And we'll find out in a subsequent slide that if there didn't happen to be any charge inside of this hollow cavity, then we might be able to say the electric field is zero, inside that cavity as well. But when I use the word inside, just so you know, we're talking about in the conducting medium itself. Now I know that for some of you, the proof that I put forth 2 slides ago may leave some doubt in your mind. So in this slide, I'm going to provide a formal proof, for you that will leave no doubt in your mind. It will really erase all doubt. First thing I'll say is that this isn't going to be on the test. Only those of you who have taken an introductory course in logic, will probably understand what's going on here. Not to discriminate, but this slide is for those who have an understanding of this stuff. So here goes. This is basically the formalization of the proof that I put forth on the previous slide, couple of slides ago, which I say is a form of proof that we will use again. It's a very powerful form of proof. So, here we go. If a conductor is in electrostatic equilibrium, then the electric field inside the conductor is zero. That's what we're trying to prove here. So I'm going to put forth 3 propositions, 3 statements. The first is what I'm going to call P. That is, a conductor is in electrostatic equilibrium. The second statement I'll call Q, and that is that the electric field is zero inside the conductor. And the third statement I'll call R is that charges accelerate. So let's look at the argument that I'm proposing here. The first premise, I'm saying that the opposite of Q, we're assuming that the electric field is not zero inside the conductor. And that notation there is, simply the notation used in some texts for the opposite of or the negative of. The second premise is that, not Q implies R, that if the electric field is not zero inside the conductor, that is going to imply that charges accelerate. And the third premise then is that, R is equivalent to, the opposite of P. In other words, if charges accelerate, that is equivalent or basically says the same thing as a conductor not being in electrostatic equilibrium. And for this argument, if premise 1 and premise 2 and premise 3, is true, then we can conclude, that P implies Q. That if the conductor is in electrostatic equilibrium, then the electric field must be zero inside this conductor. Now, so this is the basic form of the proof. What we're saying is that, Okay, I'm showing you here premise 1 and premise 2 and premise 3. Okay, if those are true, then they imply this conclusion, okay, right here, that if the conductor is in electrostatic equilibrium, then the electric field must be 0 inside. Now, how you show this, okay, this is only going to make sense for those of you who have done it, is in the form of a truth table. Okay, you set up this truth table, and I've created it here for you. We're not going to go through it in gory detail, but for those of you who, understand this stuff, take a look at it. Okay, and you'll see at the very, I kind of do, step by step here. I take each of these propositions, okay, and each of these original statements, okay, and then I build up the premises, and finally over here I'm showing you the full argument, okay, that if premise 1 and premise 2 and premise 3 are true, okay, then we can conclude what we're trying to prove here. And you recall that when you set this up and you form the truth table, okay, that if you can find that for all possible values, okay, of P, Q, and R, okay, of these statements, all possible combinations of their truth value, whether they're true or false, if that leads, okay, your final argument to be true in all cases, in all possible cases, okay, then it is a valid argument, okay? It is, okay, deductively valid. And so that's what we call a tautology here, okay, that, and this will take you some time to go through if you are inclined to do so, but it does turn out that all possible values of these statements, okay, lead to truths. That's what we call a tautology. Therefore, the argument is rock solid. Okay, it is deductively valid. We've said that the electric field inside a conductor in electrostatic equilibrium is 0. And we were careful to distinguish between the conducting material itself, okay, and a region on the interior of a conductor like this conducting shell. Now, what you see here, this garbage can in front of you, that's really what it is made out of metal, so we have a metallic conductor. Right now it is uncharged, but soon enough we're going to charge it up with the dome of this Van de Graaff generator. And if what we're saying is true, then as long as there is no other source of charge on that interior region, which there will not be, okay, then the electric field in that interior region of this garbage can should be 0. Okay, but the electric field in the exterior region will not be 0. In fact, okay, one of the properties we'll talk about is it will be perpendicular to the surface there. We'll take a look at that later. So how are we going to see this? Well, we have these, you see these pieces of styrofoam in both the exterior region and in the interior region. We would expect that the styrofoam will interact with the electric field if one exists. So in the interior region where we don't expect a field, we should see that styrofoam remain at rest. Whereas in the exterior region where we do expect an electric field to get established once we charge it up, we would expect these pieces of styrofoam to interact with the electric field. They should move in response to it. This is a precursor to this concept of shielding. When we talk about electronic shielding, we're talking about placing a metal casing around electronic components so that we can ensure that there will be no electric fields in the interior region to affect those components. So in a sense, this garbage can acts as a shield for the interior region. So let's turn on the Van de Graaff generator, and once again we expect those pieces of styrofoam in the interior region not to move, to remain at rest because there's no field there, whereas a piece of styrofoam in the external region should move in response to the electric field that gets established. So here it goes. So from the demonstration, you notice that the pith balls outside of the conductor, okay, they move when the conductor acquires this charge, suggesting that there is an electric field, okay, in the region outside of the conductor, okay, to exert an electrostatic force on those pith balls, on those pieces of styrofoam. Okay, but okay, you observe or notice that the pith balls within the cavity, okay, of the conductor, those pith balls don't move, okay, from which we can infer that there is no electric field inside in that interior region of the cavity exerting a force on them. So, and as we said on a previous slide, okay, because the electric field is a continuous entity, okay, the electric field must be zero inside the hollow cavity of the conductor, okay, as well as inside the conducting medium itself. Okay, so the conducting medium, that's really the metallic material part. Okay, but we also see here that without any charges in the interior region of that hollow cavity, the electric field is zero there as well. And this is the basis for what we call electronic shielding, which we'll explore in a little bit greater detail in the next slide. So a very important application, as we introduced in the previous slide, is what we call electronic shielding. And putting the same picture up we saw before, we see that when you have a conductive casing, basically a metal box with an interior cavity, a hollow interior cavity, so long as there are no charges within that cavity, we can say that the electric field will be zero, okay, within that cavity. So we're saying here that by placing electronic components in a conductive casing, they will be shielded from external electric fields. So why is it that a car is a pretty safe place to be during a lightning storm? Okay, or okay, as we see in this situation, and hopefully you never find yourself in this situation in life, but this is very common that when there are automobile accidents where cars strike utility lines, and very often the utility line will fall and a live wire will come in contact with the automobile, then which can produce a dangerous situation. Remember, however, that your car behaves as a conductive casing, okay, to shield you from external electric fields. And since you happen to occupy the interior region, what that means is that if there is no electric field on the inside of the car, okay, then there is no possibility of that electric field exerting a force on any charges within your body. So the source of the field is external to the car only. Okay, that is from the discharge of the cloud or from the power line itself. So if you ever did find yourself in this situation, while in a lightning storm, you're protected by being inside of your car. In the case of the down power line, so long as you don't get out of your car, you're able to drive away from under that. And if you're not, then whatever you do, don't get out of your car, okay, until help arrives. But your car will be a safe place to exist. Okay, you're electronically shielded from electric fields in that interior cavity region. The second property applying to conductors in electrostatic equilibrium is this, that any net charge on a conductor in electrostatic equilibrium resides entirely on its outer surface. So let's give a brief proof of this. Okay, assuming that we have a conductor in electrostatic equilibrium, okay, we've proven that the electric field must be zero inside that conductor in electrostatic equilibrium. What we're going to do is we're going to apply Gauss's law to any Gaussian surface that is inside that conductor. And we're going to let that Gaussian surface, we're going to draw it arbitrarily close to the surface of the conductor, since we're justified in doing that. So we can take the limit, okay, as long as that Gaussian surface is inside of the conductor, we can draw it as close to the surface of that conductor as we like. Now, for any Gaussian surface inside that conductor, okay, the flux through that surface has to be zero. Why? Because the electric field is zero, and if the electric field is zero, then that flux integral is zero. And we know from Gauss's law that if the electric flux through the Gaussian surface is zero, then we know that the charge enclosed by that surface must be zero. In which case, any excess charge can only lie on the surface of the conductor. That is the only possibility that exists here. And in the next slide, we will try to experimentally verify this fact. In this demonstration, we are trying to experimentally verify that any excess charge on a conductor in electrostatic equilibrium resides entirely on the outer surface of the conductor. So the way we're going to do it with this setup, you'll notice here we have a spherical shell here. It is hollow, and there is an inner surface to the shell and an outer surface of the shell. And you'll notice that this piece of foil I have connected to the outer surface of the shell is also connected to this electrometer, which will then be able to measure any charge that resides on the outer surface of the shell. So the way we are going to experimentally verify this, and I will explain this in greater detail, okay, and a lot slower on the upcoming slides. Okay, we now have a conducting ball, a copper ball that has been charged negatively, okay, with a Van de Graaff generator. I am going to carefully lower that ball in so I do not touch the sides of the shell. And you'll notice that the electrometer gives us a certain negative reading. Notice that if I take the ball out without touching the sides of the shell, okay, it goes back to zero, which suggests that none of that charge has been transferred. Okay, now let me lower this again without making contact. What that electrometer reading tells you is that an equal charge has been induced on the outer surface of that, okay, conducting shell. And that's what the reading is giving you. What I am now going to do is I'm going to make contact with the ball and this conducting shell. So we've now charged it by conduction. And you will notice that the electrometer reading hasn't changed. Remember, that electrometer reading is giving you the reading of the charge on the outer surface of that conducting shell. Notice when I remove the ball, okay, the electrometer reading still does not change, which suggests that all of the charge on the ball has now been transferred to the outer surface of that conductor. Okay, I can show this to you. Okay, another way here, I'm going to zero the electrometer. When I put the ball back in, okay, you will see that the electrometer reading is zero, which suggests that all of the charge there is no charge left on the ball because all of that ball's charge has been transferred to the outer surface of the conducting shell. So you see, okay, we have experimentally verified that any net or excess charge on a conductor in electrostatic equilibrium must reside entirely on the outer surface of the conductor. The demonstration that you just witnessed, okay, providing an experimental justification for this property, okay, this property that for a conductor in electrostatic equilibrium, any net charge on that conductor must reside entirely on its outer surface. Okay, the experimental justification, or really the argument behind what you witnessed in the demonstration, is really quite subtle. So I'm going to try to break it down for you here, bit by bit, piece by piece. So first of all, just a note about the electrometer in the demonstration and what it's actually measuring. Notice that the electrometer, and you can see this illustrated in the diagram here, is electrically connected to the outside surface of the conductor. And therefore, what it's going to measure is going to be the charge, okay, on that outside surface of the conductor. Okay, remember that the electrometer is what we call, as an instrument, is a high impedance voltmeter, so that it can measure the charge on some object without altering the charge distribution of that object in any kind of significant way. So we assume here that, in our case, the electrometer is electrically connected to the outer surface of the conductor, so that when it measures the charge on this outer surface, okay, it can do so without altering the charge on that outer surface. So let's get to the proof. Okay, and like I say, it's subtle. It's a bit difficult what we're trying to show here because it's so subtle. But here it goes something like this. If we can assume that an equal and opposite charge, okay, that exists on this ball is induced on the outer surface of the conductor. Okay, so remember what we're doing here is we're placing a charged ball inside of this conducting cavity. And if we can assume that, okay, whatever the charge is on that ball, that an equal charge is induced on the outer surface of that conductor, okay, and that's what the electrometer reading is going to show us, okay, that if all of the ball's charge is transferred to the conductor, okay, and that the electrometer reading doesn't change in any way, it remains the same, okay, then we can infer that all of the charge must reside on the outer surface of the conductor. Okay, so you kind of see here that this is quite subtle. Let me just say it one more time here. Okay, for the charged ball that we put inside, if we can assume that a charge of same type, okay, and same magnitude as that charged ball is induced on the outer surface of the conductor, okay, and that is what the electrometer reading is going to show us, okay, and if we can then show that, okay, independently, that by making contact with the conductor, if all of the ball's charge is now transferred to the conductor, so we know exactly how much charge is transferred, okay, and that if the electrometer reading doesn't change, okay, we are then inferring or concluding, okay, that all of the charge, okay, that was on that ball that is now in the conductor must reside entirely on its outer surface. So let's kind of go through this step by step here. So here is the charged ball. We'll say it has a negative charge, negative Q. We lower that into the conductor. Notice that there is no contact made, so we're charging by induction here. And we can then infer that a charge is induced, okay, of plus Q on the interior of the conductor, and therefore a charge of minus Q, which exactly matches that of the ball, must be induced on the outer surface of the conductor, which is what the electrometer measures, okay, and notice that gives us the electrometer reading. Now, when we remove the ball from the interior region, okay, since we have not transferred any charge, okay, therefore the charge that was induced disappears and the electrometer reading goes back to 0. So this is really the first step. Okay, we've shown that, okay, we can induce the same charge on the ball on the outer surface of the conductor, and that is what the electrometer showed us. So finishing what we started in the last slide, we now take the same charged ball, notice it's charged, okay, to minus Q just like it was previously. Now we're going to charge the electroscope and the conductor by conduction. We're actually going to lower the ball and we're actually going to make contact. And when we do so, because contact is made, charge can now be transferred. And what we would find is that, okay, if all of the charge leaves the ball and goes to the outer surface of the conductor at charge minus Q, that would now give us the exact same electrometer reading we got in the previous case with the charging by induction, what we showed on the previous slide. So when we now remove the ball, okay, from the interior chamber, okay, we see that the electrometer reading stays the same, suggesting that its reading is simply due to whatever charge is left on the outer surface of that conductor, okay, which is exactly what we saw. The amount of charge would be identical to what we saw in the previous slide if the electrometer reading is the same. Now, furthermore, okay, one last step here to prove this, we can now discharge the electrometer and the conductor. We can remove all the charge so it goes back to zero. We will once again, okay, lower the charged ball in, and noticing that, okay, the electrometer reading doesn't change, okay, suggests that the ball no longer has any charge on it, okay, and from that we can infer that whatever charge it had on it originally, all of that charge had to get transferred to the conductor, okay, and must reside on the outer surface of the conductor to give us the electrometer reading that we were able to obtain. This property of charged conductors in electrostatic equilibrium, okay, that any net charge on a conductor in electrostatic equilibrium must reside entirely on its surface. This property is quite useful in problem solving, okay, as the following example will illustrate. So in this example of a hollow conductor in electrostatic equilibrium, we're told that we have an irregularly shaped conductor that contains a hollow cavity, as you see in the diagram, and the conductor itself carries a net charge of plus 3 microcoulombs. We're told what the net charge is, but we have no idea what the charge distribution looks like. Okay, in other words, okay, how that charge is distributed, okay, throughout the conductor. We're also told that there's a positive 5 microcoulomb point charge that exists within the cavity of the conductor itself. We're asked to find what the net charge on the cavity wall is, okay, as well as on the outer surface of the conductor, of course, assuming that electrostatic equilibrium has been established. So, this is certainly a multi-step problem that we're going to have to break apart piece by piece and reason, okay, in chunks and bits here. We're going to start by considering a Gaussian surface that exists inside the conductor, okay, and encloses the hollow cavity. Now, you know that for a conductor in electrostatic equilibrium, the electric field inside the conducting medium must be zero. That's the first property we talked about today. And given that, if the electric field in the conducting medium is zero, and you'll notice that this Gaussian surface lies entirely inside the conducting medium, that means the electric field on that surface is zero. That implies, by the definition of electric flux, that flux integral is going to be zero, right? Okay, integral of E dot dA, if E is zero, the flux is zero, which then implies that the charge enclosed by the Gaussian surface must be zero, correct? That's the right-hand side of Gauss's law. So that gives us a lot of information here. Because of the positive 5 microcoulomb point charge on the interior of the cavity, how is it that we can get zero charge enclosed by the Gaussian surface? Well, we know there's got to be minus 5 microcoulombs of charge, okay, enclosed within the conducting medium somewhere. But that minus 5 microcoulombs of charge, according to this property here, it can only exist on the surface of the conductor. Therefore, we can infer that, okay, that minus 5 microcoulombs of charge must be located on the inner wall, okay, of okay, that conductor, okay, right where the cavity is located. So, given this, and the fact that we know that the total charge of the entire conductor is positive 3 microcoulombs, okay, and I say the total charge of the entire conductor, okay, that is a conductor, not a point charge in that cavity, that is separate. So given that the total charge of the entire conductor is positive 3 microcoulombs with minus 5 microcoulombs on the inner wall of the conductor, we can infer that the outer surface of the conductor must contain a total charge of positive 8 microcoulombs, okay, in order for that conductor to possess a net charge of plus 3 microcoulombs. This third very important property involving conductors in electrostatic equilibrium says that the electric field just outside the conductor, okay, that is in electrostatic equilibrium, must be perpendicular to the conductor surface. So here we'll start by giving a proof of this, and this is really the same form of proof we looked at with property 1, right? We assume the opposite of our hypothesis here and show that it leads to an inherent contradiction. So let's suppose here that we're given a charged conductor in electrostatic equilibrium, and let's assume the opposite of that hypothesis, that the electric field is not perpendicular to the conductor surface. Now we're going to show that this leads to a contradiction. If the electric field is not perpendicular to the conductor surface, this implies that there must be a component of that electric field that is parallel to the conductor surface. That's what I'll call E parallel. And that the charges on the surface of the conductor, okay, will experience this parallel force, okay, due to that parallel component of the electric field. And that force will, okay, be equal to the charge on any, okay, free charge carrier that we choose to look at, okay, times that parallel component of the electric field. Now, because all charges within the conductor are free to move, okay, the charges will accelerate as a result of that parallel force. Okay, thus, if those charges accelerate, that conductor cannot be in a state of electrostatic equilibrium. So you see here that it's led us to this inherent contradiction. We can therefore assume that, okay, our original premise must be true. That if the electric field can have no component parallel to the conductor surface and still be in electrostatic equilibrium, okay, then we are justified in saying that the electric field can only be perpendicular to the surface, okay, of the conductor. The electric field at the surface of a charged conductor in electrostatic equilibrium should be perpendicular to the surface at all points. And we're going to try to show that with this setup. You notice here we have two conductors in the form of the hoop, okay, and the cylinder. And we're going to get an electric field in the region between, okay, those two conductors, because we have one hooked up to the dome of a Van de Graaff, okay, the other is grounded. And you'll notice that in that interior region where the field should exist, I've sprinkled some grass seed. So what I'm going to do is turn on the Van de Graaff so that we charge up these conductors, and you should start to see not all, but some of those grass seeds align in the electric field. And look near the surface of the conductor, and you should see that some of these grass seeds will end up being perpendicular to the surface here. So let's turn on the Van de Graaff here. Okay, of course there are other forces, frictional forces on the seeds and seeds hitting other seeds as well. Okay, so So now we know about the direction of the electric field at the surface of a charged conductor. Let's turn our attention to the magnitude of the field. Well, it turns out that the magnitude of the electric field is given by this expression sigma over epsilon naught, okay, at any point on the conductor surface, okay, where sigma represents the surface charge density, that is the charge per unit area, okay, at that point on the surface. So we're going to apply Gauss's law to the conductor surface, and by doing so, we'll come up with a proof, okay, for the statement. How do we find the magnitude of electric fields previously? Okay, very often by applying Gauss's law. That's all we're going to do here. Now, I didn't tell you anything about the shape of the conductor, but it turns out if you look at a small enough piece of the conductor, okay, and remember, we're saying the value of the magnitude of the electric field, okay, at any point on the conductor surface. So that allows us to specify a very small piece of the conductor surface. And if we do so, a small enough piece is going to look planar to you. It's going to have planar symmetry. So we're going to identify the symmetry of the charge distribution to be planar. Okay, the second step in the process is to choose the Gaussian surface to match the symmetry of the charge distribution. Okay, and as we said previously, when we applied Gauss's law to various charge distributions of high symmetry, we said that for the planar charge distribution, the Gaussian surface of choice is the Gaussian pillbox, which is a right circular cylinder that is oriented in a certain way. And by choosing this Gaussian pillbox, these two criteria are met. Okay, the magnitude of the electric field will be constant, piecewise constant over that surface. Okay, and if the electric field is not constant, then okay, it will be perpendicular to the vector dA such that there is no flux through that part of the surface. So, as we know, it's the Gaussian pillbox. Okay, we'll define a Gaussian pillbox having a cross-section of radius r for our problem here. So we're going to draw the appropriate Gaussian surface so it passes through the point where we need to evaluate the field, which is going to be at the surface of the conductor here. I guess I could have drawn the end of the Gaussian surface a little bit closer to the conductor surface, but you can imagine that. And using the symmetry of the charge distribution to determine the direction of the electric field on that part of the surface, well, okay, we know from what we said previously, okay, that in this previous property, that the electric field has to be perpendicular to the conductor surface. Okay, so we'll draw in some field vectors here to represent that. And at this point here, we're ready to start applying Gauss's law. We're going to start by evaluating the left-hand side, that is the electric flux. And notice here that, okay, for the end cap that I'm showing you here, okay, for the top, okay, end of the Gaussian cylinder, the pillbox, you'll notice that the vector dA points in exactly the same direction as the electric field, in which case we can say that the entire the field, okay, passes through that portion of the cylinder and the flux is maximized. So in this case here, evaluating the flux integral, the electric field is going to be constant, okay, at that top end cap, and the angle between the field and that vector dA is 0, so the cosine of 0 is 1. And as always, since the electric field is constant, we take it out of the integral. So what's left of that surface integral dA is simply, okay, when we evaluate the integral, we simply get the total area of that portion of the surface, which is just the area of the circle, or pi r squared. Now you can see here in the diagram that for the sides of the cylinder, oh, sorry, let's move to the bottom end cap first. Notice that the bottom end cap is drawn within the conducting medium itself, in which case we know there's no electric field there, okay, for a conductor in electrostatic equilibrium, in which case, okay, the flux has to be 0 there as well. And, okay, as I was saying, for the sides here, I'm showing you what the vector dA looks like for the sides. Notice that it is perpendicular. Okay, we're meeting this criteria here. It's perpendicular to the field, which means there is no flux through the sides of the cylinder. Okay, that is 0 as well. Okay, so we know the total flux is simply equal to the flux through the top end cap. When we calculate the charge enclosed by the Gaussian surface, okay, we use the concept of charge density. And here the enclosed charge goes like the surface charge density sigma, okay, times the cross-sectional area of that cylinder. Okay, that is the part of the cylinder that is enclosing the charge, okay, having a value of pi r squared. All right, so last step here, of course, is to equate left-hand side with right-hand side, and when we do so, we can solve for the field magnitude. Okay, notice here that the area of our Gaussian, so the cross-sectional area of our Gaussian cylinder, pi r squared, is going to cancel out from both sides, which only makes sense. We would not expect the field, okay, to in any way depend upon the choice of our Gaussian cylinder. So when we cancel that out, we find out that the electric field has a magnitude given by sigma, the surface charge density, divided by epsilon naught. If the expression that we just derived for the magnitude of the electric field at the surface of a conductor seems a little bit unsettling to you, okay, for some reason you don't know, you're not quite sure of, okay, then perhaps this slide will clarify this for you. Think about what we talked about, what we learned when we applied Gauss's law, okay, to the case of charged insulators. So when we looked at a flat insulating sheet of charge, we showed that by applying Gauss's law, the electric field had this form sigma over 2 epsilon naught. This was for the non-conducting sheet. Whereas now, what we're saying is that when that non-conducting sheet becomes a conducting sheet, so that we have a charged conductor, now we're saying that the electric field, okay, at the surface of that conductor is twice as big. It's not sigma over 2 epsilon naught, but it's sigma over epsilon naught. Okay, is there a contradiction here? Actually, it turns out that there is not. And let's just very quickly run through the argument that we have already seen, that is by applying Gauss's law, and we'll see why there is no contradiction here. So starting with the case of the charged insulator, okay, we have a flat, really we did it for the infinite sheet of charge, so a flat non-conducting, that is insulating sheet of charge with a uniform charge distribution, okay, such that the electric field is going to, okay, due to the planar symmetry, okay, be perpendicular to the sheet, perpendicular to the plane at all points, okay, and it will produce a uniform field. And when we applied Gauss's law, we chose this Gaussian pillbox, which matched the symmetry of the charge distribution. And we showed then that when we, okay, calculated the total flux through that Gaussian surface, okay, and looking at the diagram here, we have flux through the right-hand end cap here, as well as flux through the left-hand end cap. So our total flux then, EA plus EA, was really twice EA. And when we calculated the charge enclosed by our Gaussian surface, remember this was a thin, so thin we could consider it to be a two-dimensional non-conducting sheet. So when we look at the charge enclosed, we would say that okay, the charge density sigma times the cross-sectional area here, okay, would give us the charge enclosed. That is the charge per area times the cross-sectional area would be sigma A. And therefore, when we Okay, incorporating Gauss's law here, we set the flux equal to the enclosed charge divided by the constant epsilon naught and solve for the field. That's how we came up with the sigma over 2 epsilon naught. Okay, when we now did this for the conducting sheet of charge, so the geometry is exactly the same. Okay, we're looking at planar symmetry. Okay, a plane non-conducting sheet simply becomes a conducting sheet which is charged. Okay, and when we once again apply Gauss's law, we choose the same Gaussian surface due to the symmetry. Okay, we're now looking at a thin two-dimensional flat conductor. Notice here that the charge is spread uniformly on the outer surface. This is a property of charged conductors. Okay, that any net charge must reside entirely on the outer surface. Well, for a must reside entirely on the surface. But for this sheet, there's two surfaces. There's two outer surfaces here. Okay, so we've got charge on both surfaces. In which case, when we evaluate the flux, okay, exactly the same case as before. Okay, as for the insulating sheet, right, we've got flux of the field through the right end cap as well as flux of the field through the left end cap. So the total flux is identical, okay? But here's where the difference is. When we look at the charge enclosed, you will now notice that if sigma is the charge density, okay, then we are enclosing charge on the right-hand surface of the sheet, okay, since we've got charge located there, and an equivalent amount of charge is enclosed on the left-hand surface of the sheet. So you see here we really have twice the amount of charge enclosed because charge exists on each surface. Okay, whereas for the charged insulator, okay, the charge existed uniformly distributed throughout. Okay, so the charge density, okay, meant something slightly different. And when we finish the problem and equate the flux with the charge enclosed, not forgetting about the constant epsilon naught, okay, here we find out that the electric field is twice as big, okay, sigma over epsilon naught as opposed to sigma over 2 epsilon. So hopefully you see that there is no contradiction here, okay, no paradox, but make sure you remember the difference, okay? Make sure you remember that if you're dealing with a charged insulator, the field has one magnitude, but in the case of a charged conductor, the size of the field is twice as big. So the last property that we're going to introduce today involving conductors in electrostatic equilibrium is this, that for an irregularly shaped conductor, the charge density is greatest at locations where the radius of curvature of the surface is smallest. In other words, there's an inverse relationship between charge density at the surface and the radius of curvature of the surface at that point. And in the demonstration that you're going to see on the next slide, we will experimentally verify this. As far as a proof goes, we're going to prove this in our next unit when we discuss electric potential. Okay, we'll come back and we'll give a proof of this using a slightly different quantity that we have not yet introduced. So don't feel cheated. The proof will happen, okay, just not today. Okay, try your best to sleep at night. But let's at least in this presentation take a look at an experimental verification of this fact, and you'll get a much better idea of what we mean by a measurement of surface charge density and radius of curvature. For an irregularly shaped charged conductor in electrostatic equilibrium, there is an inverse relationship between the surface charge density and the radius of curvature. In other words, for a portion of the conductor where the radius of curvature is large, the surface charge density should be small there, and vice versa. So what we're going to demonstrate is that relationship here. And you'll notice here in front of me is an irregularly shaped conductor. It is now in an uncharged state, but we'll charge it up shortly.
And you'll notice that on my left-hand side here, this portion looks like a hemisphere. It has a fairly large radius of curvature in comparison to this pointed region on the right, okay, where my right hand is, where if you can imagine this being a piece of a sphere, the radius of curvature is much smaller. So if we were to charge this up, we would expect that on the pointy side, okay, the surface charge density there should be much greater, okay, than on the more rounded side. We can measure the surface charge density using the electrometer and ice pail setup, just like we did in the lab, okay, in conjunction with the proof plane here. So let's start by charging up our conductor here with this electrostatic voltage source. So we will charge it up, and we are now ready to sample using the proof plane. So starting with the pointy side with a small radius of curvature, okay, we'll take a sampling of the charge density there, stick it into the ice pail, and to me it looks like, okay, about 8 volts is, okay, giving us a measure of the charge there. We will now take a sampling of the charge density on the larger radius of curvature side, and when we bring it in here, okay, about 5 volts, okay, there, so clearly less. So you can see here that clearly where the radius of curvature is large, the radius of curvature is small, the surface charge density is large, and vice versa.